Right now, you're standing on a rock 7,926 miles wide. Sounds big until you learn that our Sun could swallow 1,300,000 of those rocks without reaching its limit. Sounds enormous until you learn that our Sun is one ordinary, unremarkable, middle-aged star among an estimated 400 billion others crammed into a single galaxy. Sounds incomprehensible until you discover that this galaxy is itself just one of roughly 2 trillion galaxies in the observable universe alone, and that the observable universe may represent less than 1/10,000,000th of everything that actually exists beyond the horizon our instruments can reach. The true scale of the universe does not just surprise you. It demolishes every intuition your brain has ever built. It dismantles every mental model you have ever assembled about size and distance and proportion. And it leaves behind something that is both disorienting and, once you fully face it, genuinely extraordinary. Every number ahead of you is real. Every distance is verified. Every claim is physically literal, not poetic, not approximate, not rounded for comfort. If you enjoy having your sense of reality completely rebuilt from the ground up, go ahead and hit that like button and subscribe. It genuinely helps this channel keep making these deep dives for you. Now let's begin. Start with your body. You are somewhere between 5 and 6 feet tall. That height is the baseline your brain uses to interpret every spatial judgment you will ever make. When you walk down a hallway, your brain unconsciously converts the distance to footsteps. When you drive across town, it converts miles into a time your body has already experienced. When you read that the Grand Canyon is 277 river miles long and over a mile deep, something in your mind anchors that number to a felt experience, a real sensation, a memory of scale. This anchoring is not a choice. It is the fundamental architecture of human spatial cognition, built over hundreds of thousands of years of evolution, during which your ancestors needed to judge the distance to a water source estimate whether a predator was within striking range, and decide how many hours of walking separated the current camp from the next one. Your spatial intuition was calibrated for a world measured in footsteps and throwing distances. At the scales you're about to encounter, it does not fail gracefully. It does not give you a rough approximation that is merely off by a factor of 10. It simply stops working, replaced by pure abstraction, where numbers exist without any corresponding physical sensation to anchor them to. The tallest structure human beings have ever completed is the Burj Khalifa in Dubai, which stands 2,717 feet above the desert floor. If you stood at its base and looked straight up, your sense of scale would already begin to strain. It took 22 million person-hours of labour to build, 110,000 tons of concrete, 55,000 tons of steel reinforcement. From its observation deck, the horizon extends for roughly 95 kilometers on a clear day. It is a genuine monument to human engineering ambition and construction technology, and on the scale of the distances ahead, you could omit it from any honest calculation without affecting the answer. It rounds to nothing. Mount Everest rises 29,032 feet above sea level, roughly 10 times the height of the Burj Khalifa. Climbers who reach the summit describe a sky that has turned a deep indigo above them, an atmospheric pressure so low that the simple act of breathing becomes a conscious, laboured effort, and a horizon that curves with the visible arc of the planet below. They have travelled so high that they stand at the absolute edge of the breathable atmosphere. Over 300 people have died attempting this climb, and thousands more have returned with frostbite, altitude sickness, and physiological damage that persists for years. It is, by any human measure, an extreme and demanding achievement. And Everest is essentially invisible on the planet it sits on. If you shrank Earth to the size of a billiard ball and polished it to regulation standards, The resulting ball would actually be smoother than a real billiard ball. Everest, the Mariana Trench, both invisible at that scale. Everest, the Mariana Trench, the full topographic relief of the entire surface of the planet, every mountain range and ocean basin, collapses to imperceptible roughness at that scale. Earth's diameter measures 7,926 miles. 5 days, that is how long it would take to drive straight through the planet at 65 miles per hour, ignoring the 5,000-degree heat and the pressures that would crush any known material before you reach the centre. The circumference at the equator stretches 24,901 miles. A commercial airliner flying at 575 miles per hour and never landing would need approximately 43 hours to circle the globe. Your brain can almost hold that number. Almost. 43 hours is a long but comprehensible stretch of time. You've stayed awake for nearly that long before. You can imagine that much time passing. It strains, but it holds. This is the last scale at which your spatial intuition will function with any reliability at all. From here forward, the numbers will grow faster than any feeling you can summon to keep pace with them. Now leave the surface. The International Space Station orbits Earth at an altitude of approximately 253 miles, racing around the planet at 17,500 miles per hour and completing one full orbit every 90 minutes. Astronauts aboard the station watch 16 sunrises and 16 sunsets every 24 hours. The continents roll past below them. Hurricanes spiral over blue ocean. City lights blaze against the night side of the planet. Earth looks enormous from there. It fills the windows, it dominates everything. And yet the station floats barely above the atmosphere, skimming along the outermost fringe of Earth's gaseous envelope in an orbit so close to the surface that the distinction between being in space and being on Earth is almost semantic. If you shrunk Earth to the size of a basketball, the space station would orbit less than 1 millimeter above its surface. 1 millimeter. You would need a magnifying glass to see the gap. Every spacewalk ever conducted, every photograph of the blue marble, every hour of zero-gravity footage broadcast from orbit, all of it has occurred within a shell of space so thin it effectively rests on the planet's skin. 1 millimeter above a basketball. That's the full extent of humanity's permanent presence in the cosmos. The moon changes everything and not in the way you expect. Earth's nearest celestial neighbour orbits at an average distance of 238,855 miles. To make that distance physical, imagine lining up 30 Earths side by side, shoulder to shoulder in a row. The moon would sit at the far end of that line. When the Apollo astronauts departed Earth orbit in 1969 and aimed at the grey disk growing in their forward window, the journey to the lunar surface required approximately 3 days of coasting through absolute emptiness. 3 days, through nothing. 3 days with Earth shrinking from a full disk to a blue marble to a bright point in the blackness behind them. The moon growing slowly ahead. No landmarks, no sound, just the journey. During those 3 days, the astronauts travelled farther from home than any human being had travelled before or has travelled since. Radio signals between mission control and the spacecraft experienced a delay of approximately 1.3 seconds in each direction, a round trip of 2.6 seconds, a pause you could hear. When Neil Armstrong spoke his first words from the surface of the moon, the flight controllers in Houston heard them 1.3 seconds after he said them. When they responded, Armstrong waited another 1.3 seconds before hearing the reply. The conversation moved at the pace of light itself, and light was already struggling. This 2.6 second delay is the first crack in the surface of your intuition. You make phone calls and expect an immediate response. Conversations flow without noticeable lag. But at the moon's distance, the fastest thing in the universe introduces a pause you can hear, and the moon is the nearest object of any significance to Earth. the very first rung on a ladder that stretches upwards so far you cannot see where it ends. The Sun sits 92.96 million miles from Earth. Astronomers call this one astronomical unit and use it as their standard yardstick for measuring everything inside the solar system. 92.96 million miles. If you could drive a car to the Sun at 65 miles per hour without stopping for fuel, food or rests, the trip would take approximately 163 years. You would need to have started driving before the American Civil War to arrive today. A commercial airliner flying continuously at 575 miles per hour would need approximately 18.5 years of unbroken flight to cover the same distance. Even light, the fastest thing the laws of physics permit, travelling at 186,282 miles per second, needs 8 minutes and 20 seconds to bridge this gap. Every time you look at the Sun, you're not seeing the Sun as it exists now. You're seeing it as it appeared 8 minutes and 20 seconds ago. The light entering your eyes departed the solar surface before you even thought to glance upward. If the Sun were to vanish entirely at this exact moment, you would continue to see it shining in the sky, continue to feel its warmth on your face for another 8 minutes and 20 seconds before the darkness and cold arrived. The Sun you experience right now is already history. The Sun itself resists easy description without anchoring it to something you can hold in your hands. Its diameter measures 864,938 miles. If you lined up 109 Earths edge to edge, they would just barely span its face. Its volume is large enough to contain approximately 1,300,000 Earths stacked together. It accounts for 99.86% of all the mass in the entire solar system. Every other planet, moon and asteroid combined is barely a rounding error. Every planet, every moon, every asteroid, every comet, every grain of interplanetary dust adds up to barely 1/7 of 1% of the solar system's total mass. Everything that is not the Sun is essentially nothing by mass. Jupiter, the largest planet in the solar system, is so massive it could contain all the other planets combined with room to spare. And Jupiter is still roughly 1,000 times less massive than the Sun. Saturn, with a diameter 9.5 times that of Earth, is the second largest planet. If Saturn's rings were scaled to the width of a sheet of printer paper, the sheet would be roughly as wide as a football field. From Saturn's surface, if you stood on the moon Titan and looked up at the sky through its thick orange haze, the Sun would appear as a small but brilliant point of light, noticeably brighter than every other star but no longer a disk, no longer the blazing furnace that fills a summer afternoon. Sunlight at Saturn's distance is roughly 100 times dimmer than it is at Earth's surface. The warmth you feel on your skin on a spring day is essentially absent there. The solar system's outer regions are places of profound cold and deep shadow where the Sun's warmth barely registers against the background chill of space. Keep moving outward. The solar system extends enormously beyond Saturn, and the distances involved begin to stretch the word large past any useful meaning. Mars orbits the Sun at an average distance of 142 million miles, roughly 1.5 astronomical units. Its closest approach to Earth, when the two planets are on the same side of the Sun, the gap narrows to approximately 34 million miles. Even at this minimum distance, a radio signal travelling at the speed of light takes over 3 minutes to cross the void in one direction. Conversations between Earth and a rover on Mars become physically impossible. Mission controllers sending commands to the Curiosity or Perseverance rover on the Martian surface must wait anywhere from 6 to 44 minutes for a round-trip response, depending on where the two planets are in their respective orbits. During that window, the rover operates essentially on its own, making autonomous decisions about hazard avoidance and route planning because real-time guidance from Earth is not an option the laws of physics allow. The distance has made the speed of light feel slow. That is a sentence that would have been incomprehensible to every physicist who preceded Einstein. Jupiter orbits at 5.2 astronomical units from the Sun, approximately 484 million miles. When the Galileo spacecraft arrived at Jupiter in December 1995 and released an atmospheric probe into the gas giant's upper clouds, the signal confirming the probe's entry took approximately 45 minutes to reach Earth. Scientists waited nearly an hour after the event to know it had happened. Saturn sits at 9.5 astronomical units. The Cassini spacecraft spent 13 years in orbit around Saturn before its planned destruction in September 2017. Its signals took between 67 and 85 minutes to reach Earth. An hour of silence between the spacecraft and the scientists watching it. Data from Cassini's observations of Saturn's rings, its moons, its atmosphere, arrived on scientists' screens more than an hour after the spacecraft recorded it. An image of Saturn's moon Enceladus erupting water vapor into space would appear on a monitor in Pasadena, California, over an hour after the eruption it depicted had concluded. Uranus orbits at 19.2 astronomical units, roughly 1.78 billion miles from the Sun. Neptune, the outermost planet, sits at 30.1 astronomical units, approximately 2.8 billion miles away. Voyager 2, the only spacecraft to have conducted a flyby of all 4 outer planets, launched in August 1977 and did not reach Neptune until August 1989. 12 years of continuous travel through mostly empty space just to reach a planet that is still inside our own solar system. When Voyager 2 transmitted images of Neptune's moon Triton back toward Earth during the Neptune encounter in 1989, each signal took 4 hours and 6 minutes to arrive. Scientists seeing those images on their screens were watching something that had happened over 4 hours earlier, recorded by a spacecraft travelling at 35,000 miles per hour that had been in flight for 12 years. By the time any given image materialised in Pasadena, the spacecraft had already travelled several 100,000 miles from the location where it took the picture. Beyond Neptune, the solar system does not end. It continues outward into the Kuiper Belt, a broad region of icy bodies extending from roughly 30 to 50 astronomical units from the Sun. Pluto orbits within this belt at an average distance of about 39 astronomical units. The New Horizons spacecraft, which launched in January 2006, did not complete its flyby of Pluto until July 2015, a journey of 9.5 years. New Horizons travelled at roughly 36,000 miles per hour, fast enough to cross the continental United States in about 4 minutes, and it still needed 9.5 years to reach Pluto. When the spacecraft transmitted images of Pluto's heart-shaped nitrogen ice plain and its water ice mountain ranges back toward Earth, each signal took 4.5 hours to complete the journey. The first clear images of Pluto's surface arrived on Earth's screens 4.5 hours after they were captured. Pluto turned out to be far more geologically active and visually varied than anyone had predicted. The spacecraft had been in flight for 9.5 years, and the destination was still within our own solar system. Beyond Pluto and the Kuiper Belt, the solar system continues outward into the scattered disk, an even more remote region of icy bodies on eccentric orbits, and then into the vast darkness of the outer solar system where the Sun's gravitational grip begins to release its hold on the last of the bound material. The Oort cloud marks the true outer boundary of the solar system, not Neptune, not Pluto, the Oort cloud. This theoretical shell of icy bodies, loosely bound to the Sun by gravity, surrounds the solar system in a roughly spherical halo, beginning at approximately 2,000 astronomical units from the Sun and extending outward to as far as 100,000 astronomical units. 100,000 astronomical units. That distance translates to approximately 9.3 trillion miles, or 1.58 light years. It is such an enormous structure that comets falling inward from its depths and streaking past Earth on long elliptical paths may not return for tens of thousands or even millions of years after their visit. The Oort cloud is so distant that objects within it take millions of years to complete a single orbit around the Sun. Voyager 1, the most distant human-made object in the history of our species, launched in September 1977 and travelling at roughly 38,000 miles per hour, has been flying for nearly 5 decades and has covered approximately 165 astronomical units. It has not yet reached the inner edge of the Oort cloud. At its current speed, it would need approximately 300 years just to arrive at that inner boundary. To pass entirely through the Oort cloud and emerge on the other side would require roughly 30,000 years of continuous travel at Voyager's pace. 30,000 years. Agriculture appeared on Earth roughly 12,000 years ago. The wheel was invented around 5,500 years ago. Every written document, every recorded history, every named individual who ever lived fits within a period less than half as long as the time Voyager 1 would need just to traverse one structure within our own solar system. And the Oort cloud, this vast spherical shell requiring 30 millennia to cross at 38,000 miles per hour, represents only a fraction of the distance to the nearest star. This is where the solar system honestly ends. Not at Neptune, not at Pluto. Out here, where the Sun is just the brightest point of light in a sky full of points of light, and the darkness is absolute in every direction, reach the nearest star. Proxima Centauri, a dim red dwarf burning at less than 1/10 of the Sun's luminosity, sits 4.24 light-years from our solar system. 1 light-year equals 5.88 trillion miles. 4.24 light-years equals approximately 24.9 trillion miles. Written out in full, that number contains 13 digits. Your brain processes it as a number. Nothing connects it to any felt experience. Your brain will read those 13 digits and process them as a number, the same way it processes any number, and then it will quietly and automatically set aside the actual physical magnitude involved, because there is no lived experience of 24.9 trillion miles to anchor the abstraction to. So anchor it yourself. If you drove a car at 65 miles per hour without stopping, the trip to Proxima Centauri would take approximately 43 million years. If you boarded a commercial airliner flying at 575 miles per hour, the journey would take approximately 4.8 million years. Voyager 1, the fastest object humanity has ever placed in space after decades of travel, would need approximately 73,000 years to reach Proxima Centauri if it were heading in that direction. It is not heading in that direction. But if it were, it would depart in an era of modern civilization and arrive in an epoch our species, if it still exists in any form we would recognize, would have no memory of or connection to. The last ice age ended 11,700 years ago. Voyager would need to fly for more than 6 complete ice age time spans laid end to end before it arrived at the nearest star. Now make it physical. If you shrank the Sun down to the size of a golf ball, a sphere just under 1.7 inches in diameter, and placed it on a table in front of you, then on this same scale, Earth would be a grain of fine sand orbiting approximately 15 feet away. Jupiter would be a small ball bearing circling at about 77 feet. Neptune, a slightly smaller ball bearing, would orbit at around 450 feet from your golf ball Sun, just under 2 city blocks away. The Oort cloud at its outer edge would extend outward for roughly 300 miles in every direction, a gravitational territory the size of a small state surrounding one tiny dimpled sphere on a table. And Proxima Centauri, the nearest neighbouring golf ball, would sit approximately 4,300 miles away. Not across the room, not across the building, not across the continent. Across a gap spanning the width of the United States and beyond. Across a distance comparable to the span of the continental United States and then some. from coast to coast and beyond. 2 golf balls separated by 4,300 miles of absolute nothingness. That is the interstellar neighbourhood. That is how isolated individual stars actually are from one another. The night sky creates a false impression of stellar proximity. Stars appear close together in the sky because we are looking at them across a flat projection of a 3-dimensional volume so wide the perspective compresses the distances into apparent nearness. Those diagrams in textbooks showing solar systems neatly spaced along orbital lines, those illustrations of neighbouring stars as adjacent points in a grid, those are lies of convenience. They compress actual distances by factors of thousands or millions to fit on a page. In reality, the space between stars is almost incomprehensibly empty. This emptiness has a measurable character. The interstellar medium, the material that fills the space between stars, is not true vacuum. It contains matter, but the density of that matter is so low that it represents the closest approximation to true nothingness that nature produces at accessible scales. Within the Milky Way's interstellar medium, the average density of gas is approximately 1 atom per cubic centimetre. The air you are breathing right now contains approximately 27 quintillion molecules per cubic centimetre. That is 27 followed by 18 zeros. The difference between those two numbers, between the air in your lungs and the gas in interstellar space, is so extreme that the interstellar medium qualifies as a better vacuum than anything ever produced in any laboratory on Earth, using any technology that exists or has existed. If you stood unprotected in interstellar space, you would not be surrounded by darkness alone. You would be surrounded by something that falls so far short of matter that the word empty fails to capture it adequately. Profoundly, relentlessly, overwhelmingly empty. The few atoms per cubic centimetre that do exist there drift slowly through the void, occasionally accumulating into the vast molecular clouds that stretch for dozens of light years and serve as the birthplaces of new stars. These clouds, cold and dark and composed mostly of molecular hydrogen, are the raw material from which solar systems, planets, and everything that lives on them eventually emerge. Every atom in your body that is heavier than hydrogen was forged inside a star that no longer exists. The iron in your blood was synthesized in the core of a massive star that exploded as a supernova billions of years before the solar system formed. The calcium in your bones came from a different stellar explosion. The oxygen you're breathing right now was fused in the nuclear furnace of yet another star that lived and died before Earth existed. You're not metaphorically made of stardust. You're materially, chemically, atomically assembled from elements manufactured inside stars and scattered into the interstellar void through their violent deaths. The emptiness between the stars is not just empty distance. It is the medium through which the raw ingredients of planets and people were transported across light years and billions of years of time. Now widen the view. You have just crossed 4.24 light years of interstellar space to reach the nearest star. Hold that distance in your mind and then expand your perspective until the entire region around your solar system, the 20 or so nearest stellar systems within about 12 light years, becomes a single neighbourhood in a vast city. That city is the Milky Way galaxy. The Milky Way spans somewhere between 100,000 and 200,000 light years in diameter. Most recent surveys favour the higher end of that estimate, 200,000 light years. Let that sit for a moment before continuing. 100,000 light years across, minimum. If you could travel at the speed of light, the fastest speed the universe permits, it would take you 100,000 years to cross the galaxy from one edge to the other. Voyager 1, at 38,000 miles per hour, would need approximately 1.7 billion years to cross the diameter of the galaxy, a duration roughly equal to the time that elapsed between the first complex multicellular life on Earth and the present day. The Milky Way contains an estimated 100 billion to 400 billion stars. Most recent analyses favour numbers in the upper half of that range. 400 billion stars, each separated from its neighbours by light years of emptiness, each potentially surrounded by its own retinue of planets and moons. If you scaled the galaxy down to the diameter of a dinner plate roughly 10 inches across, the galactic disk would be thinner than a single sheet of copy paper. The ratio of width to thickness is that extreme. The disk is phenomenally flat relative to its width, a consequence of the galaxy's rotation, which has flattened it over billions of years, the same way a spinning ball of dough flattens into a pizza. The galactic disk is roughly 2,000 light-years thick at the Sun's position, though it flares outward at the edges and thickens toward the centre. The Sun itself orbits the galactic centre at a distance of approximately 26,000 light-years, placing our solar system roughly halfway between the core and the outer edge of the visible disk. You're not near the centre of the galaxy. You're not near the edge. You sit in what astronomers sometimes call the galactic suburbs, a moderately populated region within one of the galaxy's spiral arms called the Orion Arm or the local spur. It is, in every measurable sense, an ordinary and unremarkable position. The galactic centre is anything but ordinary. In the very core of the Milky Way, separated from us by 26,000 light-years of sears, gas, and dense dust clouds that block most of the visible light trying to cross the gap, sits Sagittarius A star, a supermassive black hole with a mass of approximately 4 million times that of our Sun. This object was confirmed through decades of patient observation. Astronomers tracked individual stars orbiting the galactic centre with instruments sensitive enough to detect motion measured in fractions of arc-seconds across thousands of light-years of distance. One star, designated S2, completes a full orbit around Sagittarius A star every 16 years and reaches speeds of roughly 2.5% of the speed of light at its closest approach. The only object compact enough and massive enough to produce those orbital velocities without being directly detectable in visible light is a black hole. In April 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A star, a photograph taken using a planet-spanning array of radio telescopes that collectively formed an instrument effectively as large as Earth. The image showed a glowing ring of superheated plasma swirling around the shadow of the black hole's event horizon, confirming what decades of indirect evidence had established. 4 million solar masses of matter compressed into a sphere smaller than the distance from Earth to the Sun, sitting at the core of the galaxy that contains us. The Sun itself orbits this galactic centre at a speed of approximately 515,000 miles per hour. That is fast by any intuitive standard. At that speed, you could travel from New York to Los Angeles in under 20 seconds. And yet, because the galactic centre is 26,000 light-years away, the Sun requires approximately 230 million years to complete a single orbit. Astronomers call this period a cosmic year or galactic year. The last time the Sun occupied its current position in its galactic orbit, dinosaurs had not yet appeared on Earth. The time before that, the most complex life on the planet was fish. In the entire 4.6 billion year history of our solar system, the Sun has completed only about 20 galactic orbits. The galaxy operates on timescales that make even the geological history of our planet feel brief. And in the course of those 20 orbits, the galaxy itself has been building, cannibalizing smaller satellite galaxies, growing steadily more massive through a process of gravitational accumulation that is still ongoing. Beyond the bright disk of stars that most people picture when they hear the word galaxy, the Milky Way possesses a vast spherical halo populated by ancient stars, globular clusters, and an invisible substance that constitutes the majority of the galaxy's total mass. This halo extends to at least 200,000 light-years from the galactic centre, substantially larger than the luminous disk itself. The Gaia Space Observatory, launched by the European Space Agency in 2013 and operational through the early 2020s, measured the precise positions and velocities of nearly 2 billion individual stars, producing the most detailed three-dimensional map of the Milky Way ever assembled. Gaia's data revealed stellar streams, those ghostly rivers of stars left behind when the Milky Way's gravity tears apart smaller satellite galaxies, at distances exceeding 200,000 light-years from the galactic centre. The existence of those streams proves that the Milky Way's gravitational influence, and therefore its physical extent, reaches at least that far. The galaxy you live in is not 100,000 light-years across. It is, depending on what you include in the measurement, at least twice that. And 85% of its mass consists of dark matter, a substance that neither emits nor absorbs light in any detectable way, whose presence is inferred entirely through its gravitational effects on the stars and gas we can see. When astronomers calculate the total mass of the Milky Way, visible stars plus gas plus dust plus all the dark matter, the figure reaches approximately 1.5 trillion solar masses. The brilliant galaxy you see in photographs is the visible frosting on an invisible structure that outweighs it by roughly 10 to 1. Not all of the 400 billion stars in the Milky Way are built alike. Red dwarf stars, which are smaller, cooler, and far dimmer than the Sun, account for roughly 70 to 75% of all the stars in the galaxy. The smallest red dwarfs contain only 8% of the Sun's mass, barely enough to sustain hydrogen fusion in their cores. What they lack in brightness, they compensate for in longevity. A red dwarf burns its fuel so slowly and so efficiently that it can shine for trillions of years without exhausting its supply. Trillions, not billions. Trillions. The universe is currently 13.8 billion years old. No red dwarf that has ever ignited has yet had enough time to exhaust its fuel and die. Every red dwarf in the galaxy is still burning. Not one of them has reached its natural end yet. The night sky you see, with its bright constellations and impressive stellar show, is dominated by rare, brilliantly luminous giant stars that are grossly unrepresentative of the galaxy's actual stellar population. The true majority of the Milky Way's stars are so dim that virtually none of them are visible to the naked eye. You have never seen most of the stars in your own galaxy with your unaided eyes. They hide in the dark, burning their slow patient fires for timescales that dwarf the current age of the universe. At the opposite extreme from the dim red dwarfs sit the blue supergiants, stars so massive and so hot that they burn through their nuclear fuel in just a few million years. A blue supergiant can contain 50 or even 100 times the mass of the Sun, with surface temperatures exceeding 30,000 degrees Kelvin. Their luminosity can outshine the Sun by factors of hundreds of thousands. A single blue supergiant radiates more energy per second than 1,000 red dwarfs produce in a year. But their ferocity is self-defeating. Burning this hot and this fast, they exhaust their nuclear fuel in a few million years, then collapse and explode in supernova events that can briefly outshine the entire galaxy they occupy. What remains after the explosion depends on how massive the original star was. The cores of moderately massive stars collapse into neutron stars, objects so dense that a single teaspoon of their material would weigh approximately 6 billion tons under Earth's gravity. The cores of the most massive stars collapse further, past any density physics can halt, into black holes. The Milky Way contains an estimated 100 million to 1 billion neutron stars and perhaps 100 million stellar mass black holes, all remnants of massive stars that lived fast and died violently over the galaxy's 13 billion year history. They drift through the galactic disk and halo, mostly invisible, occasionally revealing themselves through their effects on nearby matter or on light passing close to them. You could pass within a few light years of a black hole and never know it existed, And within those 400 billion stars, planets are everywhere. The Kepler Space Telescope, which operated from 2009 to 2018, detected over 2,700 confirmed exoplanets and identified thousands of additional candidates by monitoring the brightness of more than 150,000 stars and watching for the tiny characteristic dips in starlight caused by planets crossing in front of their host stars. The statistical conclusions from Kepler's data are staggering. On average, every star in the Milky Way hosts at least one planet. Many host multiple planets. Rocky worlds in the habitable zone, the orbital region where liquid water can persist on a planetary surface, are not rare exceptions scattered across the galaxy. They number in the tens of billions within the Milky Way alone. Tens of billions of experiments in rocky world chemistry, each running on a geological timescale, each warmed by its own star, each sitting somewhere on a spectrum between utterly barren and potentially harbouring something alive. The James Webb Space Telescope has begun examining the atmospheres of some of these worlds, searching for molecular signatures that could indicate habitability or biological activity. The detection of a biosignature gas in an exoplanet atmosphere, a combination of chemicals that chemistry alone cannot plausibly sustain without some biological process producing them, remains the next major observational frontier. If that detection occurs, it will confirm that the Milky Way is not merely a galaxy of 400 billion stars. It will be a galaxy where the chemistry of life has independently arisen in more than one location. The spiral arms of the Milky Way, the most visually distinctive feature of the galaxy's structure in every artist's rendering and every false-colour radio map, are not permanent structures made of the same stars. They are density waves. Think of a traffic jam on a highway. Cars slow down and cluster in the congested zone, then eventually accelerate and move on. The jam itself persists as a structure, moving slowly along the highway, even though the individual cars that compose it at any given moment are constantly changing. Spiral arms work the same way. The density wave rotates around the galactic centre at a different angular speed than the stars and gas embedded in the disk. Stars and gas clouds encounter the arm, slow down and bunch together in the higher density region, then emerge from the other side and continue on their independent orbital paths. The arm appears luminous because the compressed gas in the density wave triggers gravitational collapse and star formation. Newly born massive stars, blue and bright and short-lived, illuminate the arm from within during their brief brilliance before exploding as supernovae. By the time those supernovae occur, the density wave has moved on, and the next generation of gas clouds is entering the compressed zone. The spiral pattern you see in galaxies is a sustained gravitational standing wave, a pattern that maintains its appearance over billions of years, even as the matter within it perpetually cycles through. If you watched a spiral galaxy from outside over a billion-year time span, you would see the spiral pattern rotating while individual stars streamed through it, the way water streams through the standing waves of a river rapid, while the rapid's position remains roughly fixed. The galaxy's visual identity is a pattern, not a fixed arrangement of objects. Our Sun's position within the Milky Way's Orion arm is interesting for reasons that extend beyond its geometrical significance. The local stellar neighbourhood around the solar system, roughly the sphere of space within about 300 light-years of the Sun, contains somewhere between 200,000 and 300,000 stars. That sounds like a crowd. But if you distribute those stars uniformly within a sphere 300 light-years across, the average separation between neighbouring stars works out to roughly 4 to 5 light-years. The Sun's actual nearest neighbours, Proxima Centauri and the Alpha Centauri system, sit at 4.24 and 4.37 light-years respectively, consistent with that average. The local stellar neighbourhood is not crowded in any physical sense. It is a sparse scattering of isolated nuclear fires separated by years of light travel time. You could remove 90% of the stars from the local neighbourhood without producing anything that would look significantly different from the ground on a clear night. The night sky we see, with its 3,000 or so naked-eye stars, is not a view of a dense environment. It is a view of an extraordinarily thin scattering of objects. It looks numerous only because we are embedded within a thin plane of the galaxy, where the depth of the stellar distribution, combined with the sensitivity of human eyes, captures a few thousand of the nearest examples. The hundreds of billions beyond them are too distant to individually resolve. The Milky Way is also a cannibal. It has grown to its current size not only through the gradual accumulation of primordial gas, but by gravitationally consuming smaller galaxies that wander too close. It is still doing this now. The Sagittarius Dwarf Elliptical Galaxy, a small galaxy that orbits the Milky Way at a distance of roughly 65,000 light-years from the galactic center, is currently in the process of being torn apart and absorbed. Its stars have been stretched by the Milky Way's tidal forces into a long, thin stream that wraps around the galactic halo multiple times, a ghostly river of stars called the Sagittarius Stream that can be traced across a significant fraction of the sky. In a few 100 million years, the Sagittarius Dwarf will cease to exist as an independent galaxy, its stars fully incorporated into the Milky Way's stellar population. This is not a rare or exceptional event. Forensic analysis of the Milky Way's stellar populations, using the chemical compositions and orbital characteristics of stars in the halo as signatures of their origin, has revealed evidence of multiple past mergers. The most significant known event, called the Gaia-Sausage-Enceladus merger, occurred roughly 8 to 11 billion years ago, when a galaxy approximately 1/4 the Milky Way's mass at that time collided and merged with the proto-Milky Way. The remnants of that ancient galaxy are detectable today as a kinematically and chemically distinct population of stars in the inner halo. Our galaxy was built, at least in part, from the wreckage of galaxies that no longer exist as independent structures. Beyond the known satellite galaxies and their stellar streams, the Milky Way's halo contains globular clusters, dense spherical collections of 100,000 to several million stars bound together by mutual gravity, orbiting far above and below the galactic disk on paths that take them looping through the halo on timescales of hundreds of millions of years. The Milky Way hosts approximately 150 known globular clusters. Many of them are among the oldest objects in the galaxy, with stellar ages reaching 12 to 13 billion years, meaning they formed when the universe itself was less than 2 billion years old, before the Milky Way had assembled into anything like its current structure. The stars in these ancient clusters are chemically primitive compared to the Sun, depleted in elements heavier than helium, because those elements had not yet been manufactured and distributed by the supernova deaths of earlier stellar generations when the globular clusters formed. They are relics of an earlier cosmic epoch. They orbit steadily through the halo, growing slowly older. Their member stars burn at the deliberate pace of metal-poor stars, some destined to continue for billions of years more before exhausting their hydrogen and collapsing into white dwarfs. In these ancient clusters, you are looking at some of the oldest existing matter ever assembled into stellar structures, objects that predate the formation of the solar system by billions of years and that will continue to orbit through the Milky Way's halo billions of years after the Sun has died. Consider what the most extreme stellar remnants reveal about the universe's capacity for density. A neutron star packs roughly 1.5 times the mass of our Sun into a sphere approximately 12 miles across. 12 miles. The diameter of a city, containing more mass than our Sun. 12 miles. If you placed a neutron star at the center of a typical American city, it would fit within its downtown core, but that 12-mile sphere would contain more mass than 1.5 suns. A single teaspoon of neutron star material scooped from its surface and transported to Earth would weigh approximately 6 billion tons under Earth's gravity. That is the weight of roughly 1 million Great Pyramids of Giza compressed into the volume of a sugar cube. Neutron star matter is so dense that atomic nuclei are crushed together and electrons are forced into protons to create neutrons. The resulting material, sometimes called nuclear pasta due to the geometric structures it forms under extreme pressure, is theoretically the strongest material in the universe, approximately 10 billion times stronger than steel. Some neutron stars spin hundreds of times per second. The fastest known pulsar, PSRJ 1748-2446 AD, rotates 716 times per second at its equatorial surface, which therefore moves at roughly 24% of the speed of light. The magnetic fields of the most magnetically extreme neutron stars, called magnetars, reach intensities of approximately 10 to the 15th power Gauss, roughly 1 trillion times stronger than Earth's magnetic field. Powerful enough to erase the information on a credit card from a distance of a few 100,000 miles, a magnetar 200,000 light-years away on the far side of the Milky Way once released a gamma-ray flare in December 2004 so intense that it measurably compressed Earth's upper atmosphere despite the enormous distance. The universe generates objects of such extreme density and magnetic intensity that their influence propagates across a significant fraction of a galaxy's diameter. These stellar corpses, invisible except in their effects, drift through the galactic disk and halo by the hundreds of millions. You are statistically unlikely to have a close stellar neighbour that is a neutron star, but the probability is not zero. The most massive stellar cores do not stop at neutron star densities. They collapse further, past any threshold that any known physics can halt, into black holes. A stellar mass black hole, formed from the collapse of a star with roughly 20 or more times the mass of the Sun, compresses that mass into a singularity of nominally zero volume, surrounded by an event horizon, the spherical boundary within which the escape velocity exceeds the speed of light. Nothing that crosses the event horizon of a black hole, no matter, no light, no information, can ever return. The event horizon of a 10 solar mass black hole has a radius of roughly 18 miles, slightly larger than a typical neutron star, but unlike a neutron star, it is not a surface. It is a mathematical boundary in space, a threshold past which the laws of physics as currently understood break down. Beyond this threshold, the laws of general relativity predict a singularity, but physicists suspect this prediction indicates the incompleteness of general relativity rather than the actual physical reality. The true nature of black hole interiors remains unknown, one of the deepest open questions in theoretical physics. The Milky Way contains an estimated 100 million stellar mass black holes. They are distributed throughout the galaxy, mostly invisible, detectable only when they accrete matter from a companion star or pass in front of a background source with measurable gravitational lensing. You could approach one without any visible warning until the gravitational tidal forces became perceptible. Space would look entirely normal to you until it no longer could. Look at what the galaxy is really made of. Everything described so far about the Milky Way, the 400 billion stars, the spiral arms, the galactic center, the stellar populations of red dwarfs and blue supergiants, represents only a fraction of what the galaxy actually contains. Ordinary matter, the kind made of protons, neutrons and electrons that assembles into atoms and molecules and everything built from them, including every star, every planet, every living organism, and every instrument ever constructed to study the universe, constitutes roughly 15% of the total mass of the Milky Way. The remaining 85% consists of dark matter, a substance that neither emits nor absorbs nor reflects light in any detectable way, whose presence is inferred entirely from its gravitational effects on the visible matter around it. Dark matter is not a theoretical placeholder. It is not a provisional label for something scientists will eventually explain away. It is real. Its gravitational effects are measurable, reproducible, and consistent across dozens of independent methods. The evidence is overwhelming. The first compelling evidence for dark matter emerged from studies of galaxy rotation in the 1970s, when astronomer Vera Rubin and her colleagues measured the rotational velocities of stars at different distances from the centers of spiral galaxies. Based on the visible mass of those galaxies, stars in the outer regions should orbit more slowly than stars near the center, the same way the outer planets of the solar system orbit more slowly than the inner ones in accordance with Kepler's laws. Instead, Rubin found that the rotational velocity curves of spiral galaxies are nearly flat across their entire visible extent. Stars at the outer edges of these galaxies orbit just as fast as stars closer to the center. This is impossible if the only mass present is the visible mass. To produce flat rotation curves, there must be additional mass distributed throughout and beyond the visible disk, mass that does not show up in any wavelength of light. That invisible mass is dark matter, and it envelops each galaxy in a vast spherical halo extending far beyond the luminous stars and gas that we can see. If you scaled the Milky Way down to a dinner plate, the dark matter halo surrounding it would extend outward like an enormous invisible sphere, dwarfing the plate in every direction. It contains the majority of the galaxy's total mass. It determines the orbital velocity of every star in the disk. The total mass of the Milky Way's dark matter halo is estimated at roughly 1.5 trillion solar masses. Of that, approximately 1.3 trillion solar masses consists of dark matter we cannot see. The stars are the minority. By a factor of 9, the visible stars and gas that make up the recognizable galaxy, the bright disk in the astronomy posters, account for only about 200 billion solar masses. The beautiful luminous galaxy you can see in any long exposure photograph is the iceberg's visible tip, floating above an invisible gravitational mass 9 times larger than itself. Dark matter also plays a structural role at every scale above individual galaxies. Galaxy clusters like the Virgo cluster have total masses dominated overwhelmingly by dark matter, with the visible galaxies and hot intracluster gas each contributing only small fractions of the gravitational budget. The cosmic web itself, the filaments and walls and nodes that define the universe's large-scale structure, is fundamentally a dark matter structure. The ordinary matter, the hydrogen and helium gas that eventually becomes stars and galaxies, follows the dark matter's gravitational scaffolding rather than creating its own independent structure. Dark matter built the cosmic web. Ordinary matter moved into the architecture dark matter had already erected. The universe you can see is a thin luminous decoration on a vast invisible skeleton, identifying the fundamental nature of dark matter. Determining what particle or particles compose it and how those particles interact remains one of the most important unsolved problems in physics today. Understand the depth of the solar system's emptiness. If you threw a dart randomly at any point within the volume of space enclosed by Neptune's orbit, the probability of hitting any object at all, any planet, any moon, any asteroid, any comet, any debris of any kind, is so vanishingly small that it is effectively zero for all practical purposes. Neptune's orbit encloses a sphere roughly 5.6 billion miles in radius. The total volume of that sphere is approximately 7.4 times 10 to the 32nd power cubic miles. The combined volume of all the planets, moons, and major asteroids within that sphere totals a number so much smaller that comparing the two is like comparing the volume of a single grain of fine sand to the volume of the Earth. The solar system is not a collection of objects, it is a collection of absences. Objects punctuate that absence occasionally, so small relative to the distances between them that they might as well not exist from a geometric standpoint. This is why space travel is genuinely difficult in ways that have nothing to do with propulsion. It is not the objects you might hit that are the problem, it is the emptiness you must cross. Every spacecraft ever launched has spent nearly all of its flight time in regions containing nothing at all except the faintest trace of solar wind and the occasional cosmic ray. The solar system, which seems in any diagram to be a crowded family of planets arrayed along well-defined orbital paths, is in physical reality an almost perfect vacuum punctuated by specks of matter separated by hundreds of millions of miles of nothing. This emptiness has a measurable structure when examined at finer scales. The solar wind, the continuous stream of charged particles flowing outward from the sun's corona at 400 to 800 miles per second, fills the heliosphere, the vast region of solar influence that extends outward to the heliopause at roughly 120 to 125 astronomical units. Within the heliosphere, the density of the solar wind at Earth's orbital distance is approximately 10 protons per cubic centimetre. By the time the solar wind reaches Neptune's orbit, the density has dropped to a fraction of a proton per cubic centimetre, following the inverse square law as the flow expands into an ever larger volume. By the time Voyager 1 crossed the heliopause in August 2012 and entered the interstellar medium, the particle density dropped and then jumped discontinuously at the boundary, confirming the spacecraft's passage from one physical regime into another. The heliosphere is the sun's protective bubble, the region within which the solar wind's outward pressure exceeds the inward pressure of the interstellar medium. Everything inside the heliosphere is physically inside the extended atmosphere of the sun in the most literal sense. Everything outside it is genuinely interstellar space. Voyager 1 is currently the only human-made object ever to have crossed this boundary and continued outward into the local interstellar medium. Everything else we have ever built, every rocket, every satellite, every space station, every probe sent to the outer planets, remains within the sun's extended atmosphere, inside the heliosphere, never having made contact with the true interstellar environment that surrounds our solar system. The question of what Voyager 1 has found in interstellar space is itself a story about scale. At its current distance of roughly 165 astronomical units from the Sun, travelling at about 38,000 miles per hour, Voyager 1 is approximately 15.4 billion miles from Earth. Radio signals from the spacecraft travelling at the speed of light now take approximately 23 hours to reach the Deep Space Network antennas in Goldstone, California, Madrid, Spain, and Canberra, Australia. A command sent from Earth arrives at Voyager 23 hours later. Any response returns another 23 hours after that. A round-trip conversation with the farthest human artifact takes nearly 2 full days at the speed of light. The spacecraft itself was launched with computing capabilities roughly equivalent to a 1977-era pocket calculator, uses about 2.5 watts of power to transmit its signals, and has been in continuous operation for nearly 5 decades. Its data transmission rate back to Earth is approximately 160 bits per second, roughly 40 million times slower than a standard home internet connection. And despite all of these constraints, it continues to send back measurements of the interstellar medium, the local density of charged particles, the strength and direction of the magnetic field, the flux of cosmic rays, describing from the inside a physical environment that no other instrument has ever directly sampled. It is, by any measure, the most extraordinary object humanity has ever placed in space, and it is less than 0.002 light-years from Earth, a distance that rounds to zero on any scale that includes the nearest star. Zoom out beyond the galaxy. Everything you have just absorbed about the Milky Way, its 400 billion stars, its supermassive black hole, its dark matter halo, encompassing a sphere 300,000 light-years or more in radius, its tens of billions of potentially habitable worlds, is about to collapse into a single luminous point in a wider picture. The nearest galaxy comparable in size to the Milky Way is the Andromeda Galaxy, sitting approximately 2.537 million light-years from us. 2.5 million light-years. Light travelling at 186,282 miles per second has needed 2.537 million years to bridge that gap. When that light left Andromeda, Homo sapiens did not yet exist. When light now entering your eye from Andromeda first departed that galaxy, the ancestors of modern humans were just beginning to use stone tools on the plains of Africa. Homo habilis was alive then. The genus Homo was young. Every photon from Andromeda you have ever seen, in any photograph, through any telescope with your naked eye, carries information that is 2.537 million years old. You're not seeing Andromeda as it exists now. You're seeing a ghost, a portrait of a galaxy as it appeared before your species existed, preserved in ancient light that has been crossing a gap of 2.537 million light-years to finally arrive at your retina tonight. To appreciate how large that gap is, consider this. The entire Milky Way, with its 200,000 light-year diameter and its 1.5 trillion solar masses of matter, could be placed in the gap between the Milky Way and Andromeda approximately 12 times over with room to spare. The space between our galaxy and our nearest comparable neighbour is more than a dozen galaxy widths across, and yet Andromeda is practically our next-door neighbour. It belongs to the same small gravitational family as the Milky Way, a collection called the Local Group. The Local Group contains more than 80 known galaxies spread across a volume roughly 10 million light-years in diameter. Most of those 80 are dwarf galaxies, faint and small, containing anywhere from a few million to a few billion stars. The Milky Way and Andromeda are the two dominant members of the family, locked in a mutual gravitational embrace for billions of years. Andromeda is not drifting past us. It is not wandering nearby. It is falling toward us at approximately 250,000 miles per hour, closing the 2.537 million light-year gap between the two galaxies at a speed that sounds fast, but requires cosmic timescales to produce a significant result. In approximately 4 to 5 billion years, Andromeda and the Milky Way will collide. Their outer dark matter halos will begin to interpenetrate first. Then their stellar populations will begin to mix, distort, and fling stars into new orbits through gravitational interactions. The merger will take roughly 1 billion years to complete, ending with a single massive elliptical galaxy that astronomers have already given a name, Milkomeda. Despite the apparent violence of two galaxies colliding, individual stellar collisions during the merger will be extraordinarily rare, because stars are so small relative to the distances between them that the merger will proceed largely as a gravitational reshuffling rather than a physical smash-up. The Sun, if it still exists by that point, will likely survive the merger with its planets largely intact, simply relocated into a new orbit around the combined galactic centre. But even the Local Group, with its 80-plus galaxies spread across 10 million light-years, is a minor structure in the cosmic hierarchy. Zoom out further. The Virgo cluster sits approximately 54 million light-years from the Local Group. It contains over 1,300 known galaxies, packed into a volume roughly 15 million light-years across, one of the nearest and best-studied galaxy clusters in the sky. At its heart sits Messier 87, a giant elliptical galaxy harbouring a supermassive black hole with a mass of approximately 6.5 billion solar masses. That is 6.5 billion times the mass of our Sun, compressed into a region of space smaller than our solar system. In April 2019, the event Horizon Telescope collaboration released the first direct image ever obtained of a black hole, using Messier 87's central object as the target and producing a photograph of the glowing ring of superheated plasma swirling around the black hole's shadow. The image was constructed from data collected simultaneously by radio telescope stations distributed across multiple continents, turning Earth itself into a single enormous instrument. That photograph travelled 54 million light years to reach us. The light captured in that historic image left Messier 87 when the earliest relatives of modern horses were beginning to evolve on Earth, during an epoch called the Eocene, when the planet's climate was substantially warmer and tropical forests extended into regions that are now temperate. The Virgo cluster is not just larger than the local group, it represents a fundamentally different category of cosmic structure. Galaxy clusters are the most massive gravitationally bound objects in the universe. They contain not only their member galaxies, but vast quantities of superheated plasma called the intra-cluster medium, gas heated to temperatures of tens of millions of degrees by the enormous gravitational energy released during the cluster's formation and by ongoing energetic processes within it. This intra-cluster gas glows in X-ray wavelengths and contains more ordinary matter than all the stars in all the cluster's galaxies combined. The galaxies floating within the cluster are islands in an ocean of invisible X-ray bright plasma, and surrounding everything, outweighing both the galaxies and the hot gas by a factor of roughly 5-to-1, sits the cluster's dark matter halo. The total mass of a large galaxy cluster, including all its galaxies, all its hot gas, and all its dark matter, can reach into the quadrillions of solar masses. These structures are the universe's most extreme concentrations of matter, held together by gravity strong enough that even the accelerating expansion of space itself cannot pull them apart. The local group, sitting 54 million light-years from the Virgo cluster, is actually being gravitationally tugged toward it, falling in its direction at hundreds of kilometers per second. We will never reach it. The cosmic expansion is carrying the Virgo cluster away from us faster than we fall toward it. But the pull is real, measurable, and pervasive enough that astronomers must carefully account for it when trying to measure the cosmic expansion rate using local group galaxies as reference points. Step back further still. The Virgo cluster is itself embedded within a vastly larger structure called the Laniakea supercluster. Mapped and named in 2014 by astronomer R. Brent Tully and his collaborators using peculiar velocity data, the small deviations in galaxy motions caused by the gravitational pull of nearby mass concentrations. Laniakea spans approximately 520 million light-years. It encompasses the mass of roughly 100 million billion suns, distributed across an estimated 100,000 galaxies, including the Milky Way, the local group, the Virgo cluster, and tens of thousands of other systems. 100,000 galaxies, a supercluster, and it is one among many. The name comes from Hawaiian and means immeasurable heaven. It is, in retrospect, a modest understatement. Laniakea was defined not by counting galaxies within a boundary, but by mapping the gravitational flow patterns within the local universe. Every galaxy within Laniakea, including ours, is flowing toward a massive concentration of matter called the Great Attractor, a region partially hidden behind the dense dust of the Milky Way's galactic plane and located roughly 250 million light-years away. The Great Attractor pulls everything in Laniakea toward it with a gravitational influence that shapes galaxy motions across hundreds of millions of light-years. Our galaxy, our local group, our cluster, all of it is drifting in the same direction, drawn by the gravity of a mass concentration we cannot easily see because it sits behind the disk of our own galaxy. When the light from one edge of Laniakea was first emitted and began its journey toward the opposite edge, complex marine life on Earth was still hundreds of millions of years away. Fish did not exist, amphibians would not appear for another 100 million years after that. Understand what gravity does to light. One of the most powerful tools for mapping the universe's invisible mass, particularly dark matter, is gravitational lensing. Einstein's general theory of relativity predicts that mass curves space-time, and that light travelling through curved space-time follows curved paths. When light from a distant galaxy passes near a massive foreground object, a galaxy cluster for example, the cluster's gravity bends the light's path, distorting and magnifying the image of the distant background galaxy as seen from Earth. The distortion can produce arcs, rings, and in some cases multiple images of the same background galaxy arranged symmetrically around the foreground mass. The degree of distortion encodes the total mass of the lensing object, not just the visible mass but all of it, including dark matter. When astronomers calculate the mass required to produce observed lensing effects, they consistently find far more mass than the visible galaxies and hot gas can account for. The invisible component is dark matter. This result has been confirmed across hundreds of galaxy clusters using multiple generations of telescopes. The Hubble Space Telescope's deep field images, staring at small patches of sky for days or weeks at a time, reveal dozens of gravitationally lensed background galaxies in any field containing a foreground cluster, their shapes smeared into arcs by the cluster's gravity. The lensing tells you exactly how much mass is there and where it is concentrated. And it consistently tells you that most of the mass is invisible. The Bullock cluster, located approximately 3.8 billion light-years from Earth, provides what many physicists consider the single most direct visual evidence for the existence of dark matter in any individual object. This system consists of two galaxy clusters that collided at roughly 10 million miles per hour and passed through each other. During the collision, the hot intergalactic gas from each cluster, which interacts electromagnetically, slammed into the other cluster's gas and slowed down, piling up between the two clusters in a collision zone that is now visible in X-ray observations as a bright, concentrated region of superheated plasma. The dark matter halos of the two clusters do not interact electromagnetically. They interact only through gravity. When the two clusters collided, the dark matter halos passed straight through each other, unimpeded. The gas piled up in the middle. The dark matter continued through as if nothing had happened. Gravitational lensing maps of the Bullock cluster clearly show that the majority of each cluster's masses sits not where the X-ray bright gas is, not in the middle. The mass is on the outsides, with the galaxies and the dark matter that pass through. The visible mass and the gravitational mass are spatially separated in this system. The gas collision left behind a detectable signature in the middle. The dark matter continued through without slowing significantly. The result is a system that makes the existence and behaviour of dark matter visually legible in a single image. The dark matter did not stop. The dark matter did not slow. It passed through the collision as if the other cluster's gas were barely there, which, to a substance that interacts only gravitationally, it essentially was. Now consider the void between galaxy clusters. The space between the local group and the Virgo cluster, a gap of 54 million light-years, is not filled with the interstellar medium you would find inside a galaxy. It is filled with something far emptier. The intergalactic medium in the voids between galaxy groups contains on average roughly 1 atom per cubic meter, not per cubic centimeter as in the interstellar medium inside galaxies, per cubic meter. The volume of a large adult human body is approximately 0.07 cubic meters. If you stood unprotected in the intergalactic void between galaxy groups, there would be fewer than 1 atom in the volume you currently occupy. The air in the room where you are sitting contains approximately 25 trillion atoms per cubic meter. The interstellar medium inside the Milky Way holds about 1 million atoms per cubic meter. The intergalactic void holds 1. This is matter reduced to its most extreme possible thinning, while still technically being matter. Temperatures in these voids hover just above 2.7 Kelvin, barely above absolute zero. No stars are close enough to radiate warmth. The only background radiation is the cosmic microwave background, the faint afterglow of the Big Bang, cooled by 13.8 billion years of expansion from thousands of degrees to nearly nothing. If you could teleport to a random point in the intergalactic void between galaxy clusters, no star would be close enough to warm you. No galaxy would be visible to the naked eye. The darkness would be the most complete, the silence the most total, the isolation the most absolute that the physical universe permits. This emptiness is not merely a gap between interesting objects, it is the dominant physical condition of the cosmos. Most of the universe by volume looks exactly like this. The filaments of the cosmic web that connect galaxy clusters across this void are not empty either, but their contents are extraordinarily difficult to detect. The warm, hot intergalactic medium, gas heated to temperatures between 100,000 and 10 million degrees by the gravitational energy of structure formation, is predicted by cosmological simulations to contain roughly half of all the ordinary baryonic matter in the universe, distributed in tenuous threads along the filaments connecting galaxy clusters. For decades, much of this gas was missing from direct observations because it is too hot to emit significantly in visible wavelengths, and too cool and too thin to emit strongly in X-rays. Recent observations using ultraviolet spectroscopy and targeted X-ray detections have begun to confirm the filament gas predictions. In early 2025, researchers using the MUSE instrument on the European Southern Observatory's Very Large Telescope published a detailed image of a cosmic web filament connecting two galaxy groups, for the first time directly resolving the boundary between gas inside a galaxy and gas within the connecting filament. The observation matched theoretical predictions with remarkable precision, confirming that the cosmic web's bony structure is real, physically present, and can now be directly imaged rather than merely inferred. The universe's largest structures are not just theoretical constructs, they are observable, measured, confirmed by independent methods and multiple instruments, and they are organized in exactly the way that the physics of gravity acting on primordial quantum fluctuations over 13.8 billion years predicts they should be. Stand back further still. Laniakea is itself just one supercluster among many, one node in a far larger and more ancient structure that only became visible to science once telescopes were powerful enough to map the universe at genuinely cosmic scales. This structure is called the cosmic web, and it is the largest pattern of organized matter that exists anywhere in the observable universe. If you could somehow step outside the observable universe and look at the distribution of all matter across billions of light years at once, you would not see galaxies and clusters scattered randomly through space like points scattered uniformly across a page. You would see a vast, intricate network of filaments, walls and dense nodes connected by threads of dark matter and gas separated by enormous empty voids. It resembles a sponge, or the pattern of soap bubbles in a foam, or strikingly the neural network structure of a mammalian brain. The resemblance is not meaningful in any deep physical sense, but it is visually arresting, and it points to a universal mathematical truth about how networks form when similar physical rules apply at different scales. The cosmic web consists of 4 types of structures that interlock across billions of light years. The nodes are the densest regions, the intersections where multiple dark matter filaments converge, and where galaxy clusters form, anchored by massive concentrations of dark matter that have been accumulating since the earliest epochs of cosmic history. The filaments are long, thread-like bridges of dark matter and gas stretching between these nodes. They span hundreds of millions of light years in length, while maintaining widths of only 10 to 20 million light years. Vast threads, impossibly thin relative to their length. They look in three-dimensional maps of galaxy distribution like the threads of a vast luminous spiderweb. The walls are broad, sheet-like surfaces where filaments intersect, forming enormous planes containing thousands of galaxies arranged in thin sheets. And between all of these structures lie the voids, the most voluminous and least discussed regions of the universe. Cosmic voids are vast, underdense regions, typically spanning 100 to 500 million light-years across, within which the density of matter is far below the cosmic average. They contain almost no galaxies. They are the bubbles in the cosmic foam, the hollow spaces between the filaments and walls where gravity has slowly drained away the matter that once occupied these regions over billions of years of cosmic evolution. Cosmic voids occupy roughly 80% of the universe's total volume. 8 out of every 10 cubic light-years of the observable universe are inside a void. Most of the universe is empty, profoundly, structurally, definitively empty. The filaments, walls, and clusters that contain all the galaxies, all the stars, all the planets, and everything that has ever lived or thought or built anything occupy only 20% of the total volume. If you placed a pin randomly on a three-dimensional map of the universe, the overwhelming probability is that it would land in a void, not in a galaxy, not near a star, in nothing. Most of the universe is profoundly structurally definitively empty. The largest known individual structures in the universe are filaments and walls of the cosmic web. The Sloan Great Wall, discovered in data from the Sloan Digital Sky Survey in 2003, stretches approximately 1.37 billion light-years across, making it one of the largest coherent structures ever identified. If you travelled at the speed of light, crossing this wall from one side to the other would take 1.37 billion years. When the light from one side of the Sloan Great Wall was first emitted and began travelling toward the other side, complex multicellular animal life on Earth had not yet evolved. The Cambrian explosion, when the major animal body plans suddenly appeared in the fossil record, would not occur for another 80 million years. The Hercules Corona Borealis Great Wall, detected in 2013 through the spatial clustering of gamma-ray bursts, is estimated to span roughly 10 billion light-years if its full extent is confirmed. If that measurement is correct, it represents a structure so large that light travelling at 186,282 miles per second would need more than 10 billion years to cross it, a period comparable to the current age of the universe itself. These are the largest things that exist, and they are made not of a special cosmic material, but of the same hydrogen and dark matter that fills every other part of the universe, simply concentrated along ancient gravitational channels that were seeded by quantum fluctuations during the universe's first second of existence. The origin of the cosmic web traces directly back to the first moments after the Big Bang. In the initial fraction of a second during a period of extremely rapid exponential expansion called cosmic inflation, tiny quantum fluctuations in the density of the primordial plasma were stretched from subatomic scales to macroscopic scales. These fluctuations were extraordinarily small, density variations of roughly 1 part in 100,000, but they were enough. Regions with slightly higher density attracted slightly more matter through gravity. Regions with slightly lower density lost matter to their denser neighbours. Over hundreds of millions of years, this process amplified. Dense regions became denser, eventually collapsing into the first stars, which gathered into the first galaxies, which clustered along the filaments. Underdense regions emptied further, expanding into voids. The cosmic web is the direct, inevitable product of gravity acting on quantum noise for 13.8 billion years. Every thread of the web traces a line of slightly higher primordial density. Every void marks a region that started with marginally less matter than its surroundings. The cosmic web is a fossil record of quantum fluctuations that occurred during the universe's first fraction of a second amplified by gravity across 13.8 billion years into structures spanning billions of light years. The largest things in existence grew from the smallest fluctuations physics allows. The cosmic web also serves as a window into the universe's past because light travels at a finite speed. When astronomers observe the cosmic web at different distances, they are observing it at different ages. Nearby filaments and clusters show the web as it looks today. Distant ones show how it looked billions of years ago, when the universe was younger, denser, and its structures were less fully formed. The filaments were tighter then, the void smaller, the contrast between dense and empty regions less pronounced. By comparing the web's structure across different cosmic epochs, scientists can measure how it has evolved, how dark energy has influenced its growth, and whether the universe's expansion history matches the predictions of the standard cosmological model. The Dark Energy Spectroscopic Instrument, currently conducting the most ambitious three-dimensional map of the cosmic web ever attempted, has measured precise distances to tens of millions of galaxies. Its early data releases in 2024 and 2025 have produced the most detailed picture ever assembled of how cosmic structure has grown over the past 11 billion years. The European Space Agency's Euclid satellite, launched in July 2023, released its first major data sets in early 2025, revealing 26 million galaxies in just its initial deep-field observations and showing the large-scale organization of the cosmic web in extraordinary detail. These surveys are converging on a comprehensive understanding of how the universe assembled its current structure from primordial quantum seeds. And every new dataset reveals the same essential truth. The cosmos is organized on scales so enormous that individual galaxies, even massive ones like the Milky Way, are less than specks within the fabric of the web they inhabit. The expansion of the universe is perhaps the most counterintuitive property of the cosmos, and it is worth dwelling on precisely because the common mental model of it is almost certainly wrong. When astronomers say the universe is expanding, they do not mean that the galaxies within it are flying apart through space like debris from an explosion, moving through a pre-existing space that extends outward without limit. What they mean is that space itself is stretching. The distance between any two sufficiently separated points in the universe is increasing, not because those points are moving toward the edge of anything, but because the fabric of space between them is growing. There is no center to this expansion. There is no edge. Every point in the universe is expanding away from every other sufficiently distant point, and every point would look from its own vantage point like the center from which everything else is receding. This is not a product of some special status enjoyed by any particular location. It is a geometric property of the expansion itself. The rate of this expansion is described by the Hubble constant, which quantifies how fast a galaxy's recession velocity increases with distance. For every megaparsec, which is 3.26 million light-years of distance, a galaxy's recession velocity increases by roughly 67 to 74 kilometers per second, depending on which measurement method you use. The existence of a discrepancy between these two measurements, one derived from the early universe's properties as encoded in the cosmic microwave background, and the other measured directly from nearby distance indicators like Cepheid, variable stars, and supernovae, is currently one of the most actively debated problems in cosmology. The two methods should, if the standard cosmological model is complete and correct, give the same answer. They do not. The discrepancy, now reaching statistical significance beyond 5 sigma in some analyses, is called the Hubble tension, and physicists do not yet have a definitive explanation for it. It may indicate new physics beyond the standard cosmological model, new dark energy behavior, new dark matter interactions, additional species of light particles in the early universe, or subtle systematic errors in the measurement chains that have not yet been identified. it may be telling us that what we take to be a complete model of cosmic evolution is missing something fundamental. What it is not doing is going away. Every new telescope, every new measurement, every new dataset produced over the past decade has either maintained or sharpened the discrepancy rather than resolving it. The universe is expanding at a rate that our most fundamental cosmological model cannot fully explain, and the evidence for this tension is the current frontier where cosmological observation and theoretical physics are pressing most urgently against each other. Think about what the discovery of exoplanets has done to the question of scale. When astronomers speak of habitable zones around stars, they mean the orbital distance at which liquid water can persist on a rocky planetary surface, neither too close that it boils away, nor too far that it freezes permanently. The Sun's habitable zone extends from roughly 0.95 astronomical units to approximately 1.7 astronomical units, a band of space that Earth sits comfortably within. Around a red dwarf, the habitable zone sits much closer to the star, sometimes within a few million miles, because the star is far dimmer. Around a blue giant, it would extend much farther. The point is not where these zones are for any individual star. The point is how many stars have them, and how many rocky worlds sit within them. Statistical analysis of Kepler Space Telescope data produced an estimate in the range of tens of billions of Earth-sized rocky planets orbiting within the habitable zones of Sun-like and slightly smaller stars in the Milky Way alone. Tens of billions! One is a world that has been receiving starlight for potentially billions of years, potentially harbouring liquid water on its surface, potentially running chemistry that complexity can build on. And that number, tens of billions, applies to a single galaxy, one of 2 trillion in the observable universe. The number of potentially habitable worlds in the observable universe alone is effectively beyond any numeral system calibrated for human experience. 10 to the 22nd power is a commonly cited lower bound estimate. 10,000 billion potentially habitable worlds. Whether life has arisen on any of them beyond Earth is unknown. Whether intelligence has arisen is unknown. What is not unknown is that the scale of the opportunity is so immense that the question is not whether conditions for life exist elsewhere. The question is whether the chemistry of life, given sufficient time and the right conditions, always finds a way, or whether Earth's particular history is a singular accident against astronomical odds. The answer, whichever it turns out to be, will be one of the most consequential facts the human species has ever learned. Consider also the timeline of cosmic history against the timeline of human existence. The universe is 13.8 billion years old. The solar system formed 4.6 billion years ago. The first life on Earth emerged approximately 3.5 to 4 billion years ago, when the planet was barely 500 million years old. Complex multicellular animal life first appeared roughly 600 million years ago. Dinosaurs evolved approximately 230 million years ago and went extinct 66 million years ago. Our genus, Homo, is approximately 2.5 million years old. Anatomically modern Homo sapiens evolved roughly 300,000 years ago. Agriculture began about 12,000 years ago. Writing was invented around 5,000 years ago. The scientific revolution, the systematic application of observation and experiment to understand natural phenomena, began roughly 500 years ago. Modern cosmology, the field that has produced everything described in this video, has existed in its current rigorous form for less than 100 years. 1 century of serious, instrumentally grounded cosmological science has produced the picture of the universe that this video has attempted to convey. 1 century. Out of 13.8 billion years of universe. The entire length of recorded human history, every empire and civilization and cultural tradition that has ever existed in written form, fits within 5,000 years. cosmological science has existed for 2% of that span, and in those 100 years, working from the surface of one small planet, human beings have reconstructed the history of the universe from its earliest accessible state to the present. They identified the existence of 2 trillion galaxies. They detected gravitational waves from 2 black holes colliding 1 billion light-years away. They photographed the shadow of a black hole 54 million light-years distant. They measured the curvature of space across the entire observable volume with sufficient precision to determine that the total universe is at least 250 times larger than what we can see. This is what 100 years of focused observation and theory, applied by a species that evolved to throw rocks and identify edible plants, has produced. Whatever the true scale of the universe turns out to be, in all its recursive, intuition-demolishing immensity, one of its smallest temporary arrangements of atoms has managed to get surprisingly far toward understanding it, now reached the edge. The observable universe has a diameter of approximately 93 billion light-years. That number contains within it one of the most commonly misunderstood concepts in all of modern science, and it deserves careful handling before you set it aside. The universe is approximately 13.8 billion years old. Light has been travelling since the cosmos first became transparent to radiation, roughly 380,000 years after the Big Bang. You might reasonably expect then that the farthest object we could possibly observe would be 13.8 billion light-years away, since that is how long light has had to travel. But the universe has been expanding throughout that entire time. Objects that emitted light 13.8 billion years ago were much closer to us when that light began its journey. During the billions of years that the light has been in transit, the expansion of space has been carrying those objects farther and farther away. By the time the ancient photons from those objects finally arrive at our telescopes, the objects themselves have been swept outward to a current distance of approximately 46.5 billion light-years. Double that for the opposite direction, and the full diameter of the observable universe reaches 93 billion light-years. The observable universe is enormously larger than the age of the universe would naively imply. Space has been stretching while the light was in the transit. The universe expanded around the travelling photons. The destination moved while the journey was underway. This observable sphere, centred on Earth not because Earth is special but because we are the observers, contains an estimated 2 trillion galaxies. 2 trillion. The number is almost certainly an undercount. 2 trillion. The number is almost certainly revised upward as surveys improve their sensitivity to faint, distant galaxies that fall below current detection thresholds. Each of those 2 trillion galaxies contains anywhere from a few million to several trillion stars. Summing across the entire observable volume produces a total stellar population on the order of 10 to the 24th power. 1 septillion stars. A 1 followed by 24 zeros. There are more stars in the observable universe than grains of sand on every beach, every desert, every ocean floor on the entire surface of the Earth, combined. If you counted stars at the rate of 1 per second without stopping, you would need roughly 31 quadrillion years to count them all, more than 2,000 times the current age of the universe. The James Webb Space Telescope, launched in December 2021 and fully operational by the middle of 2022, has pushed the observational frontier to its most extreme limits yet. In January 2024, astronomers confirmed that a galaxy designated MOM-Z14 discovered using Webb is the most distant galaxy ever spectroscopically verified. Its light was emitted when the universe was approximately 280 million years old, less than 2% of its current age, corresponding to a redshift of 14.44. Due to the expansion of the universe during the 13.5 billion years since that light was emitted, the galaxy's current location is approximately 33.8 billion light-years from Earth. The galaxy is brighter. more compact, and more chemically enriched than theoretical models predicted for galaxies forming so soon after the Big Bang. Its existence, along with dozens of other unexpectedly luminous early galaxies revealed by Webb, suggests that star formation in the infant universe was far more vigorous and efficient than scientists had expected based on their models. The James Webb Space Telescope has not merely pushed back the observational frontier by a cosmological increment. It has revealed that the universe at early times was building large, complex structures with a speed that the models built to explain it are still struggling to accommodate. The absolute farthest boundary of the observable universe is not marked by the most distant galaxy. It is marked by a wall of light called the cosmic microwave background radiation, the oldest electromagnetic signal in existence. Released when the universe was approximately 380,000 years old and had cooled enough for the first stable atoms to form, this primordial light has been travelling for 13.8 billion years. It arrives at Earth from every direction simultaneously, stretched by the expansion of space from visible wavelengths into the microwave portion of the spectrum. It comes from a surface that sits approximately 42 billion light-years from us in all directions, surrounding the observable universe like a perfectly spherical shell. Before the moment the cosmic microwave background was released, the universe was an opaque fog of plasma so hot and dense that photons could not travel more than microscopic distances before scattering off free electrons. There was no transparent space for light to cross. No signal from that era can reach us as photons. The first 380,000 years of cosmic history are hidden behind this wall of ancient radiation, inaccessible to any optical or radio telescope that has ever been built or that could ever in principle be built. The cosmic microwave background is not just the oldest light we can detect. It is the hard limit on what electromagnetic observation can ever tell us about the early universe. Beyond the observable universe, there is more universe. How much more is a question that current physics can constrain but not definitively answer. Measurements of the universe's spatial geometry by the Planck satellite and other instruments show that space is flat to within the precision of our best instruments. Flatness implies that the universe is either infinite or so much larger than the observable portion that the curvature is below our abilities to detect. Statistical analysis of Planck's data suggests that the total universe is at minimum 250 times larger in radius than the observable portion alone, corresponding to a minimum total diameter of roughly 23 trillion light-years. If that lower bound is correct, the observable universe occupies less than 1 part in 15 million of the total cosmic volume. For every galaxy we can see, at least 15 million more exist beyond the horizon we can observe, and 15 million to 1 is the conservative estimate. The true universe could be substantially larger. It may be infinite. If the universe is infinite, it contains an infinite number of galaxies, an infinite number of stars, an infinite number of planets, and, given that physical laws appear to be uniform throughout the observable portion, an infinite number of every physically possible configuration of matter. In a genuinely infinite universe, every arrangement of particles that the laws of physics permit must occur somewhere. That includes arrangements identical to your own brain at this moment, identical to the room you are sitting in, identical to the entire observable universe as it currently exists. The implications of physical infinity are not merely strange, they are vertiginous. They undermine the concept of uniqueness itself. Whether the universe is infinite is a question that physics as currently practiced cannot answer. But the boundary of the observable universe, wherever the rest of the cosmos begins beyond our cosmological horizon, is real, physical, and shrinking, in the sense that dark energy is accelerating the expansion of space and carrying more and more of the universe beyond the speed at which light can ever reach us. Galaxies that are just barely within our observational reach today are gradually crossing the cosmic horizon as the expansion accelerates. We are living in a brief window of cosmic history when the evidence for the Big Bang, for the existence of other galaxies, for the structure of the universe, is still visible to instruments on the surface of a small rocky planet. In roughly 100 billion years, if dark energy continues to behave as current measurements indicate, every galaxy beyond the local group will have receded beyond our cosmic event horizon and faded into invisibility. A civilization arising in that distant future would look out at a sky containing only the merged remnant of the Milky Way and Andromeda, and a handful of gravitationally bound satellites, with no observational evidence whatsoever that the rest of the universe existed. The universe is slowly erasing its own history, drawing the evidence beyond reach, one galaxy at a time. We exist at the moment when the record is still intact, and beyond dark matter sits an even more pervasive mystery. Dark energy, or whatever physical reality the label currently points toward, constitutes approximately 68% of the total energy content of the observable universe. Ordinary matter, the atoms and molecules of everything you have ever touched, seen or thought about, accounts for roughly 5%. Dark matter makes up 27%, dark energy 68%. The universe is overwhelmingly composed of things we cannot directly detect, whose fundamental nature remains among the deepest unsolved problems in the history of science. Dark energy was discovered in 1998. Two independent teams studying distant supernovae found that the expansion of the universe is not slowing down as expected. It is speeding up. This was not the expected result. Nothing in the existing models had predicted it. Something is pushing space apart with increasing vigor as cosmic time advances. This was so unexpected, so contrary to the predictions of all existing cosmological models, that the discovery earned the Nobel Prize in Physics in 2011. The nature of dark energy is genuinely unknown. It may be the energy of empty space itself, a property of the vacuum predicted by quantum field theory. Though the predicted and observed values differ by a factor of approximately 10 to the 120th power, one of the largest discrepancies between theory and observation in the history of science. It may be a dynamic field that changes over time. It may be evidence that Einstein's general relativity requires modification at cosmic scales. Every serious possibility points to new physics that no current theory fully accommodates. What dark energy does is clear. It accelerates the expansion of space at large scales. It is driving galaxies beyond a certain distance away from us faster than the speed of light. Not the galaxies moving through space. Space itself expanding. This does not violate Einstein's relativity, because the galaxies are not moving through space faster than light. Space itself is expanding, carrying the galaxies along, but the practical consequence is that light emitted today by galaxies beyond our cosmic event horizon, currently estimated at roughly 16 billion light-years from us, will never reach us. Those galaxies are already causally disconnected from us, beyond any possibility of observation, communication, or physical interaction. And as the expansion accelerates, more galaxies cross this threshold with every passing year. The observable universe is shrinking in the only sense that matters for contact and observation. Its accessible portion is contracting. The fraction of the total cosmos with which we can ever have any physical relationship is diminishing, and there is no physical mechanism that can stop or reverse this process. This has consequences that extend far beyond the merely practical. In approximately 100 billion years, if dark energy continues to behave as current measurements indicate, every galaxy beyond the local group will have receded beyond the event horizon. The merged remnant of the Milky Way and Andromeda, Milkomeda, will sit alone in an increasingly dark, increasingly cold, increasingly empty cosmos, with no observational evidence available to any civilization that might exist there that anything else had ever existed. The richness of the observable universe we inhabit, the 2 trillion galaxies, the cosmic web, the billions of years of accessible cosmic history is a feature of this particular moment in cosmic time. We exist in the golden age of cosmological observation, and that age is finite. Now stand back and consider the full journey. You started this story standing on a rock 7,926 miles wide. That rock orbits a star 92.96 million miles away. That star is one among an estimated 400 billion in a galaxy roughly 200,000 light-years across. That galaxy is one of more than 80 in the local group, 10 million light-years across. The local group belongs to a cluster of over 1,300 galaxies 54 million light-years away. That cluster sits within the Laniakea supercluster, 520 million light-years in extent, containing 100,000 galaxies, all falling toward the Great Attractor. Laniakea is threaded into the cosmic web, a tapestry of filaments and voids spanning billions of light-years, organized into structures so large that individual superclusters are minor features within them. And all of this, every filament, every void, every galaxy, every star, every rocky world, and every ocean and every atom that has ever been part of anything alive, exists inside an observable sphere 93 billion light-years in diameter that represents, at most, 1/15,000,000th of the total universe. Each structure contains the previous one the way an ocean contains a single drop of water, and at every step, the transition to the next scale rendered the previous one invisible. Here is a way to feel the compression. If you represented the entire observable universe as a sphere the size of Earth, the Laniakea supercluster would be a region about 36 miles across, a mid-sized Bombay county. The Virgo cluster would shrink to about 3 miles. The Virgo cluster would shrink to less than 3 miles across, a small town. The local group would compress to about 450 feet, the length of a city block. The Milky Way itself, the galaxy containing our Sun and 400 billion other stars, would be the size of a bacterium. A bacterium inside a city block, inside a small town, inside a county, inside the Earth. And within that bacterium-sized Milky Way, the solar system would be roughly 1/1,000,000th of a millimeter across, many orders of magnitude smaller than a proton. Everything humanity has ever physically reached, every spacecraft ever launched, every planet ever photographed, every moon ever visited, all of it occupies a volume smaller than the smallest particle your microscope can detect. Inside a bacterium-sized Milky Way, inside an Earth-sized observable universe, which is itself at minimum 1/15,000,000th of what actually exists. The compression at each scale does not merely reduce the previous level, it annihilates it. This is the central truth about the scale of the universe, and it is more radical than simply saying the universe is large. The universe is recursively humbling. Every frame of reference you adopt, no matter how vast, turns out to be a negligible detail inside a larger frame you have not yet considered. There is no scale at which you can stop and say, "Now I have reached the level that matters." Every level is simultaneously enormous from below and insignificant from above. The solar system is vast beyond all human walking experience and rounds to zero on galactic scales. The galaxy is enormous beyond all stellar experience and vanishes on supercluster scales. The observable universe is the largest thing we can measure, and it may be an infinite decimal sliver of what best physically exists. This recursion is what distinguishes the true scale of the universe from mere bigness. A large number is just a large number. You can read it and move on. But the systematic collapse of every scale into the next one produces something more unsettling. It reveals that human spatial intuition is not just slightly miscalibrated for the cosmos. It is structurally, fundamentally, and irremediably inadequate. Your brain evolved to navigate distances measured in footsteps. It can stretch to encompass a few hundred miles with significant effort. Beyond that, numbers become pure abstractions, detached from any physical sensation your body can generate. You cannot feel the width of the Milky Way. You cannot sense the scale of the cosmic web. You cannot intuit the 13.8 billion year journey of a photon from the cosmic microwave background. The numbers exist in your mind as data, unanchored, ungrounded in anything your body has ever experienced. And yet here you are, a temporary arrangement of atoms on the surface of a small rocky planet, orbiting an ordinary star in the outer suburbs of one galaxy among 2 trillion. Your body was assembled from elements forged in stellar interiors that no longer exist. The iron in your blood was synthesized in the core of a massive star that exploded as a supernova billions of years before the sun ignited. That star is gone. Its iron remains in you. The calcium in your bones was produced in a different stellar explosion. The oxygen you are breathing right now was fused in the furnace of yet another star that lived and died before Earth formed. Those atoms were scattered into interstellar space by stellar deaths. They drifted through molecular clouds for millions of years. They were swept up by gravity into the collapsing disk of gas that became our solar system. They assembled through chemistry into increasingly complex structures over 4 billion years. And they are now arranged into a pattern capable of reading these words. You are not metaphorically connected to the cosmos. You are materially, chemically, atomically the cosmos, rearranged. Quantum fluctuations became cosmic structure. Hydrogen became stars. Stars became heavy elements. Heavy elements became rocky worlds. Oceans became chemistry. Chemistry became life. Life became complexity. Complexity became minds. Minds became the only thing in the known universe capable of reconstructing this entire chain from the evidence left behind by each step. You are the universe observing itself. You are matter that has become aware of matter. You are complexity that emerged from simplicity across 13.8 billion years of cosmic time and 93 billion light-years of cosmic space, standing on a rock 7,926 miles wide, able to describe the scale of the structure that produced you, with an accuracy that improves with every generation of instruments pointed at the sky. That last fact is worth sitting with. A species that evolved on the African grassland 70,000 generations ago, built on the same evolutionary foundations as the other primates, with a brain tuned for social navigation and short-range spatial reasoning, has constructed instruments capable of detecting photons that departed their sources 13.5 billion years ago. It has mapped the distribution of invisible matter across billions of light years using the bending of light by gravity. It has photographed the shadow of a black hole 54 million light years away using a telescope the size of Earth itself. It has measured temperature variations of 100,000th of a degree in the glow of the primordial fireball. It has detected the ripples in space-time produced by 2 black holes colliding a billion light-years away, with instruments sensitive enough to detect a change in distance smaller than 1,000th the diameter of a proton. This is what the species on the small rocky planet has managed to accomplish with less than a century of serious instrumented science. The scale of the universe is not a statement about human irrelevance. It never was. The universe did not build 93 billion light-years of space as a monument to the smallness of what lives inside it. It built all of that because all of that is what it takes for matter to become complex enough to contemplate itself. The vastness is not incidental. It is the mechanism. You're sitting on a rock 7,926 miles wide, orbiting a star 92.96 million miles away, inside a galaxy 200,000 light-years across, inside an observable universe 93 billion light-years in diameter, inside a total cosmos whose extent we cannot yet determine. Every scale you thought was the biggest turned out to be a rounding error inside the next one. Every distance that seemed impossible to imagine was just the entrance to a corridor leading to something larger, and none of it, not a single light year, is empty of significance. Because somewhere in this incomprehensible expanse of space and time, across all those billions of years and all those billions of light years, the universe did something that no amount of emptiness can diminish. It woke up, looked around, and began to measure itself.